Okay, good evening, Professor David J. De Los Reyes. Okay, it's August 15, 2023. The time is 9:31 p.m. Okay, my topic for tonight will be, it's tonight here in Los Angeles, California. My topic will be a long video format discussion, and this is alternating current circuit, and this will now be lesson number 21. It's lesson number 21. Okay, let's proceed. The topic is alternating current circuit, lesson number 21. This is Thevenin's Theorem example problem. The last time around, we finished the concept of Thevenin's Theorem. Thevenin's Theorem is actually a little bit advanced solution of circuitry in the computation of current. Okay, if a load is connected across an active network. Okay, let's try to bring out an example problem using the Thevenin's theorem. It's an advanced solution under circuitry. Okay, example. Find the current passing through ZL by using Thevenin's theorem. We are given a circuit. This is the circuit. Alternating current circuit. Z1, C3, and C2. And connected across it is actually CL. Okay. The problem is asking for the current passing through CL. We are given the values of C1, C2, C3, CL, and E. And the problem is asking for the current passing through CL. So by using an advanced solution, one of the advanced solutions is actually Thevenin's theorem. Thevenin's theorem is actually a simplified solution for a complicated problem. Okay, let's try to bring out the load specifications. The load specifications, all the parameters are actually impedances, right? Z1, C2, C3, and CL. The applied voltage is also alternating. Okay, I will read the values. C1 is 5 angle 30 degrees ohms. C2 is 6 angle 45 degree ohms. C3 is 10 angle 60 degree ohms. CL is 15 angle 15 degree ohms. So Z1, C2, and C3, since the angle are all positive, they are all inductive. So it could be that Z1 is a motor load, C2 is a motor load, C3 is a motor load, and CL is a motor load. And the interconnection is it's like this, right? So it seems it's a combination of a parallel and a series circuit. So if we try to bring out the solution or the current passing through AL by using an advanced solution, Thevenin's theorem, we'll do it like this. Okay, find IL. The requirement is current passing through AL. Okay, let's try to bring out the advanced solution by using Thevenin's theorem. Rule number 1 or step number 1 under Thevenin's theorem. It's always like this. Disconnect CL and solve for ATX. Okay. Step number 1 says disconnect CL and solve for TS. Meaning, we'll try to disconnect CL from the circuit. We'll disconnect it here. Right? So, if CL is disconnected, the configuration will be something like this, right? So it seems this portion here is actually an active network. You remember the last time around that there are two terminals that comes out for Thevenin's theorem. So after the disconnection, It seems this portion here is an active network. It contains impedances C1, C3, and C2, and the alternating current voltage E. Okay, so after the disconnection, we will solve for the value of ETH. ETH is actually like what we did the, under lesson number 19. We will be using our multimeter, okay? After the disconnection, we measure the voltage across this by using the multi-tester. So set it on DC or AC, then try to measure it. But theoretically speaking, if we are on the blackboard, okay, we cannot use this one, right? So we must have to bring out the solution by using Thevenin's theorem, okay? So the voltage across this after the disconnection is actually E with the subscript TH, meaning the Thevenin's open circuit voltage after the disconnection. The voltage across this is actually the open circuit voltage at the terminals, right? And as you can see, if CL is disconnected, it is just like this, right? It is just a simple series circuit, right? There should be a circulating current. And we can compute for the circulating current. Okay? Ohm's law is just voltage is equal to the product under AC circuit, current times impedance. So if we know the total impedance of this, and we know E, we could compute for I. So I will be the, is it correct? It's written already. We just replace B by ETH, and for the current, it will be the circulating current as what we did with the marking times the voltage across the voltage across C3 is actually ETH. The voltage across this is just actually the product of the current circulating times C3. This is multiplied by C3. So the formula on how to take the value of the open circuit voltage is actually the circulating current times the value of this impedance here. It's the voltage across it. Okay? We can compute for the circulating current. The circulating current will be the total applied voltage, okay, divided by the vectorial sum of C1, C2, and C3. So this is all over C1, C2 plus C3. Okay? This is the formula on how to take the circulating current. We are given three impedances in parallel after the disconnection. We are given voltage E, so we could compute for the circulating current. Okay, let's try to bring out the vectorial sum of C1, C2, and C3. Actually, I have placed already all the rectangular equivalents of the impedances. So Z1 is 4.33 plus 2.5 from this. Z2 is 4.24 plus J 4.24. And C3 is 5 plus J 8.66. Taking the sum of this, we add it vectorially to minimize the spacing to the horizontally. So Z1 plus C2 plus C3, the left hand side, equal to the right hand side. You add all the real parts, right? It's 13.57. Then you add all the imaginary parts, there will be no problem. The sign of all the imaginary parts are all plus. So this is plus J. So we add 2.5, 4.24 plus 8.66, that will be 15.24. So this is the real equivalent. Okay, we need the polar equivalent of this. So converting this 13.57 plus J 15.4, okay, we know how to change from rectangular to polar. The magnitude will be 20.535, 48.61 degrees ohms. Okay, so we now know the sum of C1, C2, and C3. So going back to this, circulating current now will be, the applied voltage is actually 230 angle 0 degree. It is always 0 degree because the voltage is always the reference vector. right? So the circulating current will be 230 angle 0 over the single equivalent of C1, C2, and C3 in terms of polars, 20.535 angle 48.61 degrees. Performing the vectorial division, it will be 11.205 angle negative 48.61 degrees. This is the value of the circulating current. The magnitude is 11.205. The angle is negative 48.61. The angle of the current is negative, so it will be an inductive load. So if we now try to go back here, okay, the open circuit voltage across this will be the current passing here times C3. It's actually the voltage across C3. Okay, so ETH now, meaning Thevenin's equivalent open circuit voltage, will be 11.205 times 10, and the magnitude is actually 112.05. Okay, the operation is multiplication, right? So we are adding the angle. The resulting angle will be 11.39 degree volts. So the magnitude of the open circuit voltage is actually 112.05 angle 11.39 degrees volts. It is 112 volts, the voltage across this, after the disconnection of CL. Okay, step number 2. We will compute for the open circuit impedance. We will be using again our multitester. This multitester doesn't have the impedance measurement, but there are multitesters which could measure impedance. So if we try to short out the source, okay, if we short out, it has no more effect, right? So under step number 2, we short out any voltage source inside, then we try to compute theoretically the open circuit impedance across this. And in actuality, you could use your impedance method to measure the impedance across this. But under Thevenin's theorem, if we are on the blackboard, okay, after the disconnection or shorting out of the voltage source, the diagram will be something like this, right? There was this voltage source initially, but under step number 2, we short it out to compute for CTH. We short it out, so there's a short over here, no more power source, right? So what comes out are just simply 3 impedances, and luckily Z1 and C2 are in series, and the single equivalent of this is in parallel with this. So to compute for the Thevenin's open circuit impedance, okay, we try to combine first C1 and C2. C1 and C2 are in series, right? So I designate that as CA, and if we try to compute for CA, after the simplification, the magnitude is 10.902, 38.18. So actually, after the simplification, this will now just be a simple one. This is now CA, right? The single equivalent of C1 and C2. And if you try to see it, this CA here is in parallel with this. Okay? So to compute for the impedance over here, we know the, what we call this, the equation and how to take the impedance of 2 parallel impedances, right? That is 1 over CTH equal to 1 over CA plus 1 over C3. If you don't want to use impedance, just place it here, YTH equal to Y1 plus Y2, right? If you don't want to work with impedances. But in here, I presented impedance solution, right? Because after taking for YTH, to compute for CTH, impedance and admittance are reciprocal, so this should be 1 over YTH. That will be the other solution. But the solution I presented here is actually, I just substitute the values of CA and C3. So actually, I didn't use this one. But this should be the second solution. If you want the admittance solution, I will erase this one, right? And if we try to convert this one, okay, for parallel impedances which are only two, CTH, okay, if we try to simplify this, the fraction is different, right? So this should be CA plus C3 over CA times C3. And if we try to compute for this, CTH now will be the product CA-C3 over C1 plus C3. If there are only two impedances in parallel, okay? But if there is three, that's another thing. We better use the so-called admittance method, right? So the Thevenin's open circuit voltage now will be the product CA-C3 over the sum of CA plus C3. Okay, it's just a matter of what you call this substitution now. We can compute for the product of CAC3, right? What comes out is 109, angle 98.80. And for CA, what's it? Oh, the sum of CAC3. This is the rectangular, C3, this is the rectangular. We take the sum. What comes out is 20.49 angle 18.76 degrees. So going back to this formula here, okay, the product is 109, right? Is it 109? C3? Yeah, 109.02 over angle 98.18, and the sum is 20.49 angle 18.76. Performing this, 109 over 20 is the open circuit impedance is 5.32. The angle is it should be 98.18 minus 18.76. Okay, what comes out is 49.42 degree ohms. So the open circuit impedance across this, or just in case we use the impedance meter, what will come out should be 5.32 magnitude. By using the impedance meter, we cannot just use the multidistant. Better use an exclusive impedance meter for computing or for measuring impedance value, right? So, but theoretically, what comes out for the open circuit impedance is 5.32 angle 49.42 degrees. Oh, it's good. Then the last part of the solution, okay, it's only 3 steps. Okay, solve for the Thevenin's open circuit voltage, solve for the open circuit impedance, then step number 3, draw the Thevenin's equivalent. Thevenin's equivalent, according to Mr. Thevenin's, the computed open circuit voltage should be connected in series with the open circuit impedance, then try to reconnect the load, right? The load in which the current is being asked. Try to reconnect. So what comes out, if we try to reconnect, it's just again a simple series circuit, right? The open circuit impedance and the load are actually in series. So if we try to compute for the current passing here, we know the Thevenin's open circuit voltage, right? So we just take the sum of this. It's 19.6, 23.84. Therefore, the current passing through the load CL will be 112. Okay, the Thevenin's value is 112.05. Where's it? This is. Okay, all over the sum of Thevenin's open circuit voltage and load, which is 86, 19.6. The magnitude is 19.6 over 19.6. And the resulting current passing through the load will be 5.715. The angle will be 11 minus 23.84. The angle will be negative 12.45 degree amperes. The angle of the current is negative. This is a lagging load. This is a motor load, right? So supposed to be the angle of the current lags the applied voltage, right? So the current passing through here, by using Thevenin's theorem, it is 5.715, angle negative 12.45 degree amperes. Okay, that's it. Okay? So that will be the solution by using Thevenin's equivalent, one of the advanced solutions under the study of circuitry. Okay, take note of this problem because the next time around, we will be discussing another advanced solution, maybe in Norton's theorem, and we will be solving again same problem. And that problem still will be asking the current passing through here. So by using another advanced solution, okay, we should produce same load current as 5.715. So it means to say we are presenting two advanced solution solving one problem, so supposed to be the answer will be just one. So take note of this. On the Norton's theorem, again we will be solving this one. And the problem is again asking for the current passing here. So by using Norton's, we should produce this current IL 5.715. Okay, that's it guys. For those of you who are thinking of electrical engineering, if you want to subscribe to my channel is at youtube.com/@prof.davidj.de. If you want to share it, please click share. This is one of the advanced solution of circuitry problems under alternating current circuit. Thevenin's theorem example problem. Okay, good evening from Los Angeles.